Okay, assalamu alaikum wa rahmatullahi wa barakatuh. Let's begin the lecture. Today we're going to continue with the chapter 6 where we talk about random processes. Last time we introduced the random process and we had a few examples on that, and we talked about the types of random processes quickly, and then we introduced the we introduced the independence and stationarity, and also we talked about the CDF and PDF of random processes, and also we began talking about the mean, which is one of the properties of the PDF for a random process. So we're going to continue talking today about the mean at the beginning of this lecture as shown here on the screen. So just to refresh your memory, the mean or the expected value of the random process x of t will be given in this equation right here, which is the integration of x times the PDF of the random process x of t, okay? And also if the random process was a function of g, then as we did that back in chapter 3, I believe, we just take the integration of the function itself, g x of t, times the PDF, as shown here on this in equation 2. So let's take an example here. For example, if we have this sine wave x of t, which is a sine omega naught t plus theta, and where a is a constant and theta is a phase, okay? And theta here is a random variable. Theta is the random variable, and it's uniformly distributed between 0 and 2 pi, okay? And of course, it means this sine omega naught t plus theta, this is a function. So theta is a function of g, let's say. Let's assume this is the g theta t. This is the function right here, okay? So it's very straightforward like we did before, nothing new. Now we need to find, of course, the PDF for theta. Of course, since it's given to us as a uniformly distributed, if you go back to last lecture or previous lectures, you can see that the PDF for theta in this case is going to be 1 over 2 pi, because it's basically it's 1 divided by b minus a, where b 2 pi in this case, a is 0. So after you plug in all the information, and of course the integration is going to be limited between 0 and 2 pi, and we all know how to do this, then you will end up with this equation 6, and obviously cosine omega t plus 2 pi and cosine omega t plus 0 are the same. 2 pi and 0 is the same, so these will cancel each other, and then you will end up with 0. So the mean in this case is 0. Okay, now this is related to the mean. So we had 2 examples on the mean. This example, and last lecture we had another example. And let's talk now about something called autocorrelation, okay? And as you can see here, the autocorrelation function, it's given by rxx t1 t2 for random process. It's the expected value of 2 realization, okay, or 2 group members, x1 and x2 in this case, or t1 and t2, okay? They have 2 different time functions, okay? It's the same random process, but they have 2 times different, okay, t1 and t2, okay? So obviously we just take x1 and x2 based on their times, and you do the integration, okay? This is basically the expected value. Now if we go to page 2, and if we define the time difference between the time period t2 minus t1, it's tau. Okay, tau is the time difference between t2 and t1, okay, then equation 7 can be written in this fashion, okay, which is T1, and we replace T2 by T1 plus tau, because the time difference between 2 and 1 is tau, okay, and the expectation is going to be the autocorrelation is going to be in terms of tau only, okay. You can see that proof in the book, or there's an exercise related to that. We're not going to go through this proof, but we're going to go with this. We're going to say that if the time difference between the two realizations is tau, okay, it means we can say the autocorrelation is going to be in terms of tau, okay. And now we have a few properties related to the autocorrelation in terms of tau. Now, when tau is equal 0, it means the expected value, obviously here, the expected value is going to be xt, since t1, now here will be t1 will be xt squared, which one, this one is equal to the average power. So when tau is equal, when the time difference is 0, there's no, of course, obviously there's no time difference. It means the autocorrelation here is the average power or the second moment of x of t. And also the autocorrelation of tau and minus tau, autocorrelation here is even function. It's just like sine and cosine, okay, or like the cosine sine, okay. So it's negative tau or tau, it's the same thing. And also the absolute value of tau, the absolute value of the autocorrelation in terms of tau, it's less or equal to the absolute value, less or equal to the average power, because we said the average power is equal to autocorrelation when tau is equal 0, which is the maximum. The autocorrelation will be at max when tau is equal 0. So the absolute value of this one is either less or equal to autocorrelation when tau is equal 0. And of course, the absolute value here, because we talked about, if you go back to the second one here, because it's an even function, so it's either negative or positive, it's going to be less or equal to this function right here. Okay. Now we're going to talk about first order stationary process. First order stationary process. We did mention something about stationarity last time, okay? And we did say that the function, if the function is not affected by the time difference, okay, it's not going to change with the time. It means it's stationary, okay, which is basically like a random variable, okay? So a random process is called stationary to order one. If its first order density does not change with a shifted time origin, which given in equation 9 right here. So if we have this first order PDF, the PDF for the random process, and T1 was shifted by delta, okay, and this shift, there's no difference between this one and this one, which means, you know, it's not going to change. If you shift it from one place to another, you know, at this time or that time, there's no change. It means it's stationary, okay? It's not going to change, okay? Otherwise, it's going to be, of course, non-stationary, okay? Now, in this case, we can say that this PDF, in this case, is independent of T1, okay? It's independent of T1 because, you know, T1 or the time is not impacting the PDF, okay? So because, you know, if it's not going to change as the time elapses, it's not going to change if the time changes, okay? It's not going to impact it by the time change. It means it's independent of the time. And the process or the random process mean in this case is constant, which is it's just like a random variable, okay? It's constant. The second topic we're going to introduce is the second order White-Stein stationary, the second order and White-Stein stationary, okay? So we talked about the first order density function. Now we're going to talk about the second order density function, where we have two realizations here. Okay, again, the same thing we're saying here, a process is called stationary to order 2 if its second order density function satisfies this, which means T1 or T2 are not changed by, by delta, by changing the time, okay? It's basically the same as equation 9. Equation 9 is dealing with the first order density function, and equation 11 is dealing with the second order density function, okay? So now we just mentioned wide sense stationary, okay? So a second order stationary process is a wide sense stationary if it meets these two conditions. So we have two conditions for a random process to be a wide sense stationary. So if you are given a function or random process and you want to determine whether a wide sense stationary or not, the first thing you will make sure that the expected value of the random process is constant. The expected value of the random process is constant, which means it's not going to be impacted by shifting in time origin, okay? Would satisfy equation 9. And the second one is the expected value of the two random processes x1, x of t1 times x of t1 plus tau, where tau, of course, the time difference between t1 and t2, as we talked about, it's equal to the autocorrelation in terms of tau, which is basically like this one here. So we want to show two things to make sure the random process is a wide sense stationary. First of all, the mean is constant. It's not depending on time. And the autocorrelation is independent of time. It's only depending on tau only. Okay? That's all we need to do, okay, to make sure that the random process is wide sense stationary. And of course, this here on the top of page 3, if we have more than, if we want to talk about a third order, now we talked about the first order, the second order, if we're going to talk about the third order density function and so on and so forth. This one we're going to refer to as strict sense stationary, and we're not going to go through this. The first two are good enough, okay? So let's take this example here. We are given a random process. It's a cosine function, a cosine omega naught t plus theta, where a and omega naught are constant, okay? And the variable here is theta. The random variable is theta. And it's uniformly distributed over 0 to 2 pi, which is basically just a moment, please. It's similar to this example we just did at the beginning of the lecture, right here. The only difference, this is a sine function and the other one is a cosine. Okay? Now we need to show that x of t, or x of t is a wide sense stationary, okay, WSS. So like we said, we have two conditions to meet. The first condition is the mean is constant. The second condition is the autocorrelation is in terms of tau only, okay? So the first one is, we can do that quickly, like we just, similar to the example we just did at the beginning, okay? The only difference is that one is a sine and this one is cosine. Otherwise, theta, the PDF of theta is 1 over 2 pi. So we do the integration like we just did. And obviously we can show that the mean of x of t is 0, which is obviously constant, equation 14. Now, the second condition is we need to show that the autocorrelation is in terms of tau. It's independent of time, okay? So in this case, we replace T1 and T2 with T plus tau, where tau, like we said before, is the difference between the two times, T1 and T2. So the expected value, which is, this is the definition of the autocorrelation, is going to be equal to x of t times x of t plus tau, okay? Now we replace x of t with this function right here, x of t, and of course, the second part, it's going to be t plus tau, okay? And as shown in equation 16. Now we just use a trick identity right here on the left-hand side, where when you have the cosine theta, cosine beta is equal half cosine theta plus beta plus half cosine theta minus beta. Okay, so you apply this here, very straightforward. You learned that in previous courses, of course, nothing new. And you will end up with equation 17, okay, because the difference will be this result, cosine omega tau, which is constant, of course. Now, if you remember back in chapter 3 or other chapters, the expected value of constant, we take the constant out. So this will be out, and also this is constant. So the only difference is now we're going to find the expected value of cosine 2 omega t plus omega 2 omega naught t plus omega tau plus 2 theta. Now we do the integration on this from 0 to 2 pi. And this is very obvious that the integration over a full period for cosine is going to be 0. Even graphically, if you do the graph for cosine, okay, you know, any cosine or sine, when you do graphically, okay, without doing the integration actually, you can tell right away it's 0, because the area under a full period of cosine is going to be 0, right? So there's no need to do the integration. But to prove that, you can do that, okay? So this part is 0. So from equation 19, we're going to end up with only this part. And as you can tell here, from equation 20, the autocorrelation, it's only in terms of tau, it's independent of t. So since x of t, the mean for x of t is constant, and also the autocorrelation for x of t is depending on tau only, is independent of t, then x of t, we can see it's wide since stationary. Okay, that's simple. So, I mean, it's very straightforward. The only thing you have to do, just two conditions, and that will tell you whether it's wide since stationary or not. Do we have any questions today related to these notes or these today's lecture? Okay. If you guys don't have any questions, we'll talk to you inshallah next week. يعطيكم ألف عافية.
يعطيك العافية دكتور.
Okay, شكرا.